In our third example, we are going to look at something little bit more complicated. So consider the question where we want to find the fourth root of root 3 plus I. The method stays the same. So I am going to start off by stating that z to the 4, so we're going to let z to the 4 be the same as root 3 plus I. That would mean that r to the 4 cis 4 theta is the same as root 3 plus I. Now, unlike the other two examples, I can't just take a factor out to try to equate r to the 4. So I really need to break this up into its real and imaginary components. So that would be r to the 4 cos 4 theta plus I r to the 4 sine 4 theta equals root 3 plus I. Then I need to go and find the modulus of root 3 plus I so that I can find the value of r to the 4. So r to the 4 is going to be square root of root 3 squared plus 1 squared, or 2. So now I can rewrite my complex number as 2 cos 4 theta plus I times 2 sine 4 theta equals root 3 plus I. Now I can equate my real and imaginary parts of the complex number. 2 cos 4 theta is equal to root 3, and 2 sine 4 theta is equal to 1, or cos 4 theta is equal to root 3 on 2, and sine 4 theta is equal to 1 on 2. Now we know from our right angle triangle trig that the angle that results in root 3 on 2 for cos and 1 on 2 for sine is 30 degrees, or pi and 6. So 4 theta is equal to pi and 6. Again, we have two ways of looking at this. We can start by adding 2k pi, then dividing both sides by 4, and adding and subtracting lots of 2k pi on 4s until we get our 4 solutions. Or we can look at this as dividing the Argand diagram into 4 sections. So 2 theta equals pi on 24. I am adding lots of 2 pi on 4s and subtracting until I get my 4 solutions. Either way, we end up with the same result. So for my thetas, I end up with pi on 24, then pi on 24 plus 2 pi on 4, then from pi on 24 I subtract 2 pi on 4, because if I added I would go beyond the domain of theta, and then I subtract 2 lots of 2 pi on 4s, which is the same as 4 pi on 4, which is the same as pi. So my 4 thetas end up being pi on 24, 13 pi on 24, negative 11 pi on 24, and negative 23 pi on 24. And therefore my final 4 roots are z1. Now we better go back and check this. I had r to the 4 equaling 2, so r is 2 to the power of a quarter. So our z1 is 2 to the power of quarter cis pi on 24, z2 2 to the power of a quarter cis 13 pi on 24, and so on. And that's how we find the complex roots of a complex number using de Moivre's theorem.